The focus of this video is on triangles that have diagrams that look like this, to be honest. Something that we would call a side splitter, or maybe something that has parallel lines running through a triangle. So a diagram that looks like this creates a situation of similar triangles. So I first want to make sure that you can see both of the triangles in the picture. So I'm going to draw them as two separate, okay? So the first triangle is this top one, and it is labeled with A, D, and E. And the second triangle would be the larger triangle, labeled with A, B, and C. So we have two sets of triangles here. And the first thing you want to know is, what do we know about them? And I'm going to argue that they are similar. And it's through really that all the angles are the same. And we can find that through properties of other things that we know. So the first thing I want to mention is this angle A up here. So if these two triangles, one was sitting on top of the other. So for example, if I were to color the back triangle green, let's say, right? So you've got the green one sitting in the background. And then I put a very, let's say a clear appearance triangle on top, and it's orange. That's sitting here. Both of those are sharing an angle, and that's angle A. They're both sitting one on top of the other. So the first angle that we can say is congruent in our picture is angle A, and that's because of, remember, the reflexive property. Anytime they are sharing a side or an angle, we can use the reflexive property to say that they're congruent. The next part that we have, though, would be, looking at the parallel lines. So when we look at parallel lines, we want to double check that we have a transversal. So we want to stay on the same transversal. So I have transversal 1, this blue one, and then I have transversal 2, this pink one. Now, when I do parallel lines and transversals, I can't mix. I can't pull an angle from a blue one and then say it's congruent to one on a yellow one, because it doesn't work that way. So what you can notice, though, is that we have a blue to pink angle here, and we have a blue to pink angle here. So we're arguing then that this angle D and this angle C are congruent, and that is by, just to review vocabulary, corresponding angles, okay? And then we have the same thing with the yellow and pink. So we've got a yellow and pink angle here, and a yellow and pink angle here. So we've got 3 dashes here and 3 dashes here. So essentially, through parallel lines and the reflexive property, we have two triangles that have 3 congruent angles. So this would mean that these two triangles, one that sits on top of the other, or one that's been split by a parallel line, is said to be similar. Once we start adding measurements to them, what you can notice is that you can set up two proportions. You can set up a part to whole or a part to part. So when you set up a part to whole, what that means is you're taking one of the segments and you're relating it to the entire length of that side. So my part would be 6. I could have also used 4, and my whole would be 10. And that would be just one side. And then I'd have to go to the other side and use that part to whole. So if I'd match up my colors here, I could set up proportions like, and there's really two different ones. I could set up 6 to 10, and over here 4.5 to 7.5. I could have done 4 to 10 and 3 to 7.5. So that part to whole, me going from a small segment to the entire segment, that's one type of proportion. And when you do these, they all equal out. They always work, right? This is 45, this is 45. So every time you do part to whole, it works great. But the great thing about these side splitters, especially when you've got these parallel lines, is that you can also do part to part. So what do I mean by part to part is that we're not taking into consideration those full lengths at all. We are just looking at these smaller segments. So we're looking at 4 and 6 and 3 and 4.5. So if I set this up, green to pink, what you'll notice is that these also work to show that these are proportional. So we can be a little creative and choosy when we're solving for X, because we can decide if we're doing part to part or part to whole. So let's look at a few examples of this. So the first one here is I don't even have any whole lengths. And so I don't even want to consider anything other than part to part. So if I highlight my like parts, I've got these two parts are, correspond to each other. And these two parts correspond to each other. So when I set up my part to part proportion, I'm doing 12 to 16 equals 15 to x. There are lots of ways that you can set up this proportion. You just need to make sure that you keep things consistent. So then when we do this, we would multiply across here, and then we would multiply across the other way, right? So we get 12x is equal to, so sorry, I don't have this off the top of my head. So 15 times 16 is 240. And then I would divide by 12, and I get x equals 20, which means this side length right here is 20. You can see in example 2 that we're doing a little bit of part to whole. The x is representing the whole length. So if we're going to do part to whole on the bottom, I need to know the whole length of this side, which I can get. I have both parts. All I have to do is add those and get 9. So when I do this bottom one, I need to make sure that I use the same parts though. So stay in the same lane, either the pink lane or the blue lane, which really the pink lane is the one that's going to help me because they all have numbers there. So I'm going to relate 2 to x, so there's my part to my whole, and then I'm going to do 4 to 9, staying in my lane here, not switching lanes. So this is 18 equals 4x, and when I divide by 4, I get 4.5. So that's the length of the entire segment here. If I needed to know the smaller segment, I could just take away this 2, and the remaining would be 2.5. So let's look at some more numerical examples and also ones that get a little bit harder. So we're putting in a larger triangle with multiple side splitters. So you can think about this as we've got this blue triangle here. And then we've got one larger than that. We've got this pink triangle here. And then we've got one even larger than that. We've got this green triangle here. So again, remember that we have in our back pocket that we can use part to whole or part to part whenever we want to. They both work. So the first thing that I'm asked for is DF. So DF is right here. So that is a part. It's not a whole length of a triangle. It's just a section of it. And so I want to set up a part-to-part proportion for DF. So when I do that, I'm first going to name DFX. And I need to find, parts that will help. Well, the first thing I need to do is I need to stay in my lane. And so that tells me I need to use 1. And the only other parts that I have are the ones prior. So if I look in front, I have a 4 and a 5 that are also parts. So I think those are the lengths that I'm going to use. So for DF, I'm going to do, let's see, our part to part. So 4 to X, I went to the blue and then out, and then 5 to 1. So when I do that math, I get 4 equals 5X. And when I divide by 5, I get 0.8 equals X. So DF is now, I'm going to erase my X, and I'm going to put in the DF is 0.8. All right, so when I go for my next one, I want FB, which is this segment right here, another segment, right? I'm going to name this X now. So for FB, I want to find the length of that segment. So again, the first thing I want to do is stay in my lane and look at, I have to use this too. I really like using that front blue triangle and sticking with things that are given, just in case like I made a mistake on my math. It's not like a domino effect where they're all wrong because I messed up something earlier. So I'm going to stick with 4 and then jumping to X, and then I'm going to do 5 and then jumping to 2. So I get 8 equals 5X, and when I divide by 5, I get X equals 1.6. So now it gets a little tricky because we've been doing part to part for everything, which is great. But now I'm being asked a question about line FG. And line FG is tricky because when I look at line FG, which is this line right here, this is it's not a section of the pink triangle, it's an entire side of the pink triangle. And so to do that, I really think you need to look at the blue and pink triangles. So if I make a blue triangle and I make a pink triangle and I label the sides of those blue and pink triangles, I would see that I have measures on the blue. I have 4, 5, and 3. On the pink one, I now have to do a little adding. So I had to start here, and it's 5 and 1 that make up that pink length. So that's 6. And it's 4 and 0.8, right? This and this that make up that. So this is 4.8. And I want to know this. Well, now when I look at it like this, I'm doing these whole entire lengths. Now I can set up really any proportion I want. I think I'm going to use the 5 and 6 just because there's no decimals. So I'm going to do 5 to 6 equals 3 to x. When I do that, I get 18 equals 5x. And when I divide by 5, I'm getting x is equal to 3.6. So this length here is 3.6. I would do something very similar for the blue to green. So if I keep my pink or my blue triangle there and I make a green triangle right over here on this side and I fill in the information that I know, on my green triangle on the bottom, it's this whole length here, which is 5 and 1 and 2, which is 8. And this green length is all the way across, so I'm adding 4 plus 0.8 plus 1.6, and that is, what is that, 6.4? And then this is my new x. So if I look at these two triangles, again, I can set up another proportion, maybe going, 8 to 5 and x to 3. So 8 to 5 and x to 3 gives me 24 equals 5x. And when I divide that by 5, I get 4.8. So you just have to be careful when we're doing part to part and where those parts come from, or part to whole. When are we looking at the whole length of a triangle? And as we break this up more, it gets tricky. You have to pay attention and really ask yourself those questions before you get started. The last connection that these side splitter pictures have is to algebra. So don't be scared if you see multiple X's or maybe expressions in your picture. Set up exactly what you've been doing. So in this case, I can clearly see that this is a part to part. I've got these two parts here. I've got this part and this part here. So I'm going to set up my normal proportion. So 4 to X equals X over 9. And then I'm going to do the math the same. So 4 times 9 is 36. X times X, this was eye-opening today, but when you multiply two X's, you get X squared. So at this point then, to solve for a square, we take the square root of both sides. So I'm getting that X is equal to 6. So that means this side is 6 and this side is 6. Perfect. This last one can be like maybe a little scary, but you don't have to be. When I look at this question, I see a part, and then I see the whole thing given. So I think this is a great example of a part to whole. So when I do this, I'm getting X plus 8. That's my part over the whole 25 equals the part 12 to the whole 20. So when I first do this math, 25 times 12, I'm getting 300. And now this is the tricky thing. This is 20 times X plus 8. You have to distribute the 20 to both numbers. So 300 equals 20x plus 160. For there, I'm just solving for x. So I subtract 160, and I get 140 equals 20x. Divide by 20, and I get x equals 7. So really, how does that help me? Well, I still want to find this length here. So if x is 7, 7 plus 8 is 15. And if this is 15 and the whole thing is 25, then this is 10. So I do think that, as you practice this and get more experience with it, I do think it'll click. It will make sense. It's still the same proportions. It's just really figuring out if it's part to part or part to whole that you're dealing with. If at any point you have any questions, please do not hesitate to ask.